Hi everybody, and welcome back to LS30. So let me summarize, first of all, where we are right now. We understand the concept of state space. And state space is shark tuna space, or shark tuna plankton space, or glucose insulin space, or whatever. We understand that a point, x0, y0, represents the state of the system at a time. And then we learned that we have a model. And the model is in the form of a change equation. X prime equals some function of xy, y prime equals some other function of xy. And we understand that this model gives rise to a vector field. And the vector field gives us, at any point x0, y0, it gives us the change arrow, which is the change vector x0 prime, y0 prime. And where do we get x0 prime, y0 prime from? Plugging in x0, y0 into f and g and getting x prime and y prime. And that's our change vector. We understand the theorem, the fundamental theorem on the existence and uniqueness of solutions, which says that there is a unique red trajectory. And we understand Euler's method, that we can take small, successive, straight line approximations and get as close to the red curve as we care to get. So that's the picture. And now, in a certain sense, we are totally armed and ready. We develop a model, we generate the state space and the vector field, we use Euler's method to approximate the trajectory, and we see the behavior of the system. Now, you might ask, well, is that all? Is this what we're going to do now? We're just going to develop models and press the Euler's method button and see where the trajectories go. And of course, in a lot of cases, that is what happens. But what we're going to do now is to learn some very powerful techniques that enable us to get a kind of a master view of this situation. After all, there is a certain problem with what I said. I definitely traced out, I used Euler's method to trace out a trajectory from a single initial condition, right there. Now, what about this initial condition? What about this initial condition? What about an initial condition 20 yards into positive x? How many initial conditions can I look at? And when can I stop? Wouldn't it be great to have a big picture and to understand the lay of the land in terms of where can these trajectories be going, and to have a kind of a master view of the whole state space instead of doing 50,000 Euler's method simulations? And the answer is we can. And that's our subject today, is using certain mathematical techniques to get the big picture in state space. So let's start with an example. And I want to start with an example in 1D. And as a matter of fact, for the next half hour, 40 minutes, everything we're going to do is in 1D because it's a special case and it shows us cool things. So our 1D model is going to have, obviously, a single state variable in a one-dimensional state space. And I want to use as my example the vector field of what is called the logistic model. And that's x prime equals bx times 1 minus x over k. And you remember that this is the birth rate and this is the crowding factor. And I want to start to look at the vector field on that state space. So let's start off by redrawing that state space really big. Here is 0. And I want to start now to draw some change vectors onto this state space. So let's take a point here. And let's say this is x equals k over 2. So let's look at the vector field at the point x equals k over 2. So what is its value? Its value is b times k over 2 times 1 minus k over 2 over k. So what is that? That's bk over 2 minus bk over 2 times 1/2, which is equal to bk over 2 minus bk over 4. Now, bk over 2, b and k are positive. So bk over 2 minus bk over 4 has got to be greater than 0. You're dividing a positive quantity by 1/2, and then you're taking 1/4 of that, and 1/2 of it is going to be bigger than 1/4 of it. And a bigger number minus a smaller number is a positive number. So we know that the vector field here is a positive number and is pointing to the right. Let's take another test point here. Let's take x equals 2k. So let's figure out the vector field at x equals 2k. So what is it? It's b times 2k times 1 minus 2k over k. So that's 2bk minus, multiplying that in, 2 times 2bk. So we have a quantity minus twice that quantity. That quantity is going to be less than 0. And so the change vector here has to be negative. For huge values of x, can the change arrow change signs? And the answer is no, because the vector field is bx. Let me multiply these terms out. Bx minus bx squared over k. Now, if x is huge, the x squared is going to dominate. X squared is just going to be much larger than x when x is large. And so it's always going to be negative. It's always going to be pointing to the left, even at x equals 10 million. So that's point number 1. We can see what's happening far away. But now I want to study the extremely important phenomenon, that's our really subject here, which is, okay, over here, x prime is less than 0. Excuse me, it's positive. X prime is greater than 0. And over here, x prime is less than 0. It's negative. So if it's negative over here and positive over here, and we're going from negative to positive, there's a theorem that says you can't go from negative to positive or from positive to negative without passing through 0. And so somewhere here, there has to be a point at which x prime equals 0. And it's easy to find that point. After all, we just said x prime equals bx times 1 minus x over k. That's the general form of the vector field. And we're asking now to find the point for which x prime equals 0. Well, let's just set 0 equals bx times 1 minus x over k and find the values of x that make that equation come out to be 0. A point like this is a super important point, and it is called an equilibrium point. And that is defined at a point such that x prime equals 0. Now, as I said, it's easy to find that here, and it's especially easy to find it because we left this equation in its factored form. This equation, x prime equals bx times 1 minus x over k, has this term times this term. And we know from elementary algebra, we know that if the product of two terms is going to be 0, then at least one of them has to be 0. So we have two choices here. This can be 0, or the second term can be 0. Well, let's deal with the first case, which we haven't talked about yet. If bx equals 0, can you solve this equation for x? Well, yes, b is not 0, and bx is 0, so that's got to be x equals 0. And what that's telling us is that the vector field at x equals 0 is 0. In other words, x equals 0 is an equilibrium point of this vector field. Great, that takes care of the first clause. Now, if x is not equal to 0, then we can divide by it, divide out bx. And now we want to ask, when is this term equal to 0? Well, 1 minus x over k equals 0 exactly when x equals k. X equals k, this is 1 minus 1. That's 0. So x equals k is the second equilibrium point of this differential equation, which we found by simply setting the vector field equal to 0. It's no longer a differential equation. It's now just a piece of high school algebra. 0 equals bx times 1 minus x over k. Find x. So we did. We found two x's, x equals 0 and x equals k, are the two equilibrium points of this system. So we found the equilibrium points of this vector field by just setting x prime equal to 0 and find the x's that satisfy. Now I say x's. There were in this case 2. And we found it by saying, well, either this is 0 or this is 0. In other words, we used the factored form of this equation to make a quick and dirty, this has got to be 0 or that's got to be 0. Now, I could, of course, have multiplied out the vector field, which we often do for other purposes, and said bx minus bx squared over k, and now I got to find the zeros. I have a quadratic equation. And then you could say, well, I could divide by x, assuming it's not equal to 0, and then I just have a linear equation. But maybe in another circumstance, I would have I couldn't simply divide out by x. And then I would have to solve a quadratic equation. I don't want to have to solve quadratic equations. So it's best to leave this in the factored form because finding the zeros is easy. However, there is a virtue, there is an asset in looking at the full written out equation for the vector field after we multiply everything out, because that tells us the order of this equation. This equation, the biggest exponent is 2. So this is what's called a quadratic equation for that reason. And there is a theorem called the fundamental theorem of algebra that says that a second degree equation, a quadratic equation, has exactly 2 roots. And this one does indeed. X equals 0 and x equals k. Those are the 2 roots of that quadratic equation. I want to go a little deeper into this, and I want to introduce a new model, which we're going to see a lot of. And the model is called the Ali effect. And it says that it agrees with this, and it says, yes, there is a growth rate. Yes, there is a carrying capacity. But it also postulates that there is a threshold called A, which is such that if the population, in this case, the x variable, does not reach the threshold, it will then die. And that's another effect that's not in the logistic model. So we now have a new model. And the new model is going to be x prime equals bx times 1 minus x over k, just like before. But now there's going to be, and there's a time sign, and now there's going to be a new term. And that new term is going to be x over a minus 1. Now, what is the meaning of that term? Well, let's just study it. If x is less than a, then x over a is less than 1. If this expression is less than 1 and you are subtracting 1 from it, it is going to be negative. So this term is going to be negative whenever x is less than a. And conversely, when x is greater than a, this fraction is greater than 1. Subtract 1, it's greater than 0. So we have another equilibrium point there. And we now have 3 equilibrium points in this system because this is a product of 3 terms. And this can be 0 when x is 0. This can be 0 when x is equal to k. And now I'm assuming that a is less than k. It's going to be 0 when x equals k. And it's going to be 0 when x equals a. So we now have 3 equilibrium points, 0, a, and k, corresponding to the 3 terms. And you'll notice that if I multiplied out these 3 terms, I have an x times an x times an x. This is yada, 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 x cubed, yada, yada. And so it's a cubic. Don't even think about trying to solve the cubic. That's a nightmare. Leave it in the factored form and it's totally easy. But if you multiply it out, you see that it's a cubic, and you know that a cubic equation has exactly 3 roots, and there they are, 1, 2, 3.